The universe was not supposed to be old enough for this. Not for cities of stars compressed into almost nothing. Not for structures so dense, so organized, so violently efficient that even now, more than 13 billion years later, they feel less like a beginning than a system already underway. And yet that may be exactly what James Webb caught. Not just ancient starlight, not just another remote galaxy dissolved into a red smear, something tighter, harder, more unsettling. 5 compact knots of light inside a galaxy so distant that what we see left it when the universe was only about 460 million years old. Webb, with the help of gravitational lensing, resolved that distant arc into what researchers identified as 5 young massive star clusters. Each appears extraordinarily compact, with sizes around a parsec and masses on the order of 1 million suns. That detail matters more than it first seems to, because the shock is not simply that stars existed that early. We already knew the young universe was making stars. The shock is that it may already have been making architecture. There is a comforting story human intuition likes to tell about beginnings. First there is simplicity, then slow accumulation. Then, after enough time, enough cooling, enough trial and error, complexity arrives. We imagine the early cosmos as raw material, thin gas, weak structure, unfinished physics, a rough draft of reality, vast darkness waiting to become organized. But distance has always made the early universe look gentler than it was. From far enough away, violence compresses into glow, density collapses into brightness, structure becomes blur. A thing can be ferocious up close and still arrive at Earth as almost nothing. One faint stain in a black field, one bent crescent of light, one tiny red wound in the dark. That is part of what makes this observation so unnerving. The farther back we look, the more the universe tends to simplify itself in appearance. Galaxies that may contain internal extremes collapse into unresolved smudges. The eye receives softness. The physics may be anything but soft. So when Webb looked toward the lensed galaxy now known as cosmic gems, the real event was not merely that it saw something old. Countless instruments have seen old light. The real event was that nature briefly stopped hiding the scale of what was happening inside it. A foreground galaxy cluster warped space-time strongly enough to magnify the background system, and Webb had the resolution to use that accident of gravity like a second instrument. Without that combination, this would likely have remained what the early universe so often becomes in our data, suggestion without texture. Instead, the blur broke open, and inside it were not diffuse hints of star formation, not a vague stellar haze, but compact concentrations of light so intense and so confined that they force a harder reading of the cosmic dawn. The early universe was not waiting to become structured, it already was. That sentence lands harder when you slow down enough to feel what it means. 1 million suns is a large number in any context. Packed into a region on the scale of a parsec, it stops sounding like a population and starts sounding like pressure. Not empty space with a few stars sprinkled through it. Not a young galaxy casually beginning to glow. Something more compressed, more local, more consequential. A star-forming event so concentrated that the usual emotional language of the distant universe begins to fail. Because distance makes things abstract. A galaxy 13 billion light-years away sounds almost philosophical. It sounds too large to feel. But a parsec is not philosophical. A parsec is tight. A parsec is spatial discipline. A parsec is the difference between there were stars and something forced matter into a brutal kind of closeness. And closeness changes everything. When stars form in loose distribution, their light is impressive. When they form in compact clusters, their light becomes pressure. Radiation has somewhere to accumulate. Stellar winds begin to matter more violently. Heat, ionization, turbulence, feedback, all of it sharpens. Compression is not just a geometric detail. Compression is a change in regime. That is why this is more than a beautiful telescope result. It is a crack in an old mental model. We tend to imagine the young universe as broad and unfinished because young feels like it should mean fragile. We project childhood onto physics. We project immaturity onto matter. We assume that because the universe had only recently emerged from its first long darkness, the structures inside it must still have been hesitant, simple, half-formed. But the universe does not respect emotional metaphors. Youth, in cosmic terms, does not mean innocence. It does not mean softness. It does not even mean slowness. Sometimes it means conditions so extreme, so concentrated, and so unforgiving that matter organizes itself with a speed that feels almost offensive to human expectation. That is the deeper disturbance hidden inside these tiny points of light. They do not merely say that stars appeared early. They say the machinery of assembly was already running hard. And once that possibility enters the frame, the meaning of first billion years starts to shift. It stops sounding like a preface. It stops sounding like the universe clearing its throat before the real story begins. Instead, it begins to look like one of the most decisive construction phases reality ever went through. The interval when gas, gravity, radiation, and time were already negotiating what kinds of structures would survive, what kinds would dominate, and how quickly darkness could be punctured from within. This is where the discovery stops being merely observational and becomes psychological. Because most people can accept that the universe is vast. Most people can accept that it is old. Even strangeness, in the abstract, is easy to accept. What is harder to accept is that our intuition about beginnings may be fundamentally untrustworthy. That what feels like it should have taken ages may have happened almost immediately. That complexity did not politely wait for comfort. That structure may have arrived before our mental picture was ready for it. The young universe, in this view, was not an empty hall waiting for furniture. It was already under construction, loudly, densely, under pressure. And those 5 knots of light matter because they are not cinematic inventions. They are measured objects, real enough to estimate, real enough to constrain, real enough to force theory into a narrower corridor. Researchers describe them as young, massive clusters embedded in a galaxy magnified by lensing, potentially offering a direct look at the kinds of dense stellar systems that may be connected to the ancestors of today's globular clusters. Even the broader review literature around JWST's first billion years results points to a young universe that appears more efficient and more structurally mature, in some ways, than the older picture allowed. That does not mean every mystery is solved. It does not mean one observation rewrites cosmology by itself. The responsible reading is narrower and, in a way, more powerful. The dawn is starting to look less primitive than our old blur made it seem. Webb is not giving us license for exaggeration. It is removing excuses for simplification, which makes the next problem unavoidable. If these objects were really there, compact, massive, already forming in a universe this young, then the first question is no longer whether the early universe made stars. It clearly did. The harder question is why we were so bad at seeing what that really looked like. Because for most of the history of astronomy, distance has not just hidden the early universe from us. It has cleaned it up. And the moment you realize that, the darkness changes. It no longer looks empty. It looks censored. The blur was never the truth. It was only the limit of our sight. The blur was never the truth. It was only the limit of our sight. That matters because distance does something deceptive to the universe. It does not just make things faint. It strips away their internal argument. A galaxy that may contain pressure gradients, violent stellar winds, clustered birth sites, metal-poor gas, and localized radiation fields arrives to us as one softened patch of light. The farther back we look, the more reality gets flattened into appearance. Ancient structure becomes a silhouette of itself. For a long time, that flattening controlled the story we told about the first billion years. We could see that galaxies existed. We could estimate rough brightness, rough redshift, rough mass. We could infer star formation, but inference is not the same thing as contact. The problem was never simply that the early universe was far away. The problem was that, at those distances, the most important differences between kinds of structure begin to collapse. A loose spray of stars and a compact engine of star formation can both dissolve into the same unresolved glow if your sightline is weak enough. And unresolved glow is dangerous, because once detail disappears, intuition rushes in to replace it. We start supplying the missing texture ourselves. We imagine the young cosmos as diffuse because the image is diffuse. We imagine gradual assembly because the picture looks smooth. We imagine primitive galaxies as shapeless first attempts because, from our distance, shape itself has been erased. This is one of the quiet ways astronomy humbles us. The universe is often not misleading, but our measurements can be merciful. They soften what, in truth, may have been much harsher. The early universe was especially vulnerable to that mercy. By the time its light reaches us, space itself has stretched it. Expansion drags ultraviolet and visible light outward into the infrared. Surface brightness fades. Small scales become tiny angles. Even with remarkable telescopes, a galaxy seen only a few 100 million years after the Big Bang occupies almost no room on the sky. It is there, but barely. And what little room it occupies is not enough to casually reveal its internal anatomy. So when people imagine astronomy as a steady march of better pictures, they miss the real difficulty. The challenge is not just seeing farther, it is seeing past simplification. It is forcing reality, at impossible distances, to surrender detail it would rather keep compressed. That is why the Webb result is not merely another record for looking deep. Plenty of observations are deep. Depth alone does not solve this problem. Webb became decisive here because the issue was not reaching the early universe, it was dissecting it. The difference sounds technical. It is actually existential for the story. If all you know is that a remote galaxy contains stars, you have one version of the cosmic dawn: early light, early assembly, an understandable beginning. But if you can resolve that light into compact, massive clusters, only about a parsec across, packed within a region under 70 parsecs, then the emotional meaning of early galaxy changes. The question stops being whether the universe had switched on. The question becomes what kind of intensity was already hiding inside the switch on itself. That shift is easy to miss because astronomy often sounds abstract when stated cleanly. A parsec, 1,000,000 solar masses, redshift 10.2, less than 70 parsecs, younger than 50 million years, minimal dust attenuation, low metallicity. These are scientific descriptions, and they matter. But in human imagination, they need translation. A parsec is not much room. 1,000,000 suns is not a gentle population. Low metallicity means matter that has not yet been heavily reworked by long generations of stars. Younger than 50 million years means these systems are, cosmically speaking, almost newborn. Put that together, and the image becomes less like a distant galaxy, and more like localized furnaces embedded in a young gravitational framework, pouring radiation into surroundings that have had almost no time to become ordinary. That is the truth distance usually erases. It erases the difference between illumination and compression. And compression is everything. Because a galaxy does not experience star formation as a pretty photograph. It experiences it as energy released somewhere, in some geometry, with some density, into gas that will be ionized, heated, stirred, and in some places expelled. A diffuse stellar population and a tightly packed stellar cluster do not do the same thing to their environment. Not emotionally, not dynamically, not radiatively. The same amount of starlight, arranged differently, becomes a different kind of event. This is one reason researchers care so much about these objects as possible protoglobular clusters. The scientific excitement is not just that they are old, it is that they may be gravitationally bound, physically compact systems formed under conditions severe enough to produce structures that could persist. The Nature paper explicitly frames them as consistent with bound stellar systems and as candidates for protoglobular clusters, while also arguing that star cluster formation and feedback likely helped shape galaxies during reionization. That phrase, shape galaxies during reionization, is the larger pressure waiting behind the image. Because if compact clusters were common, or even just important in that era, then we're no longer talking about decorative details inside early galaxies. We're talking about one of the mechanisms by which the early universe changed its own state. That is a far more dangerous story than Webb found stars very far away. It means the blur had been hiding agency. For years, one of the central questions about the first billion years has been how the universe went from mostly neutral hydrogen, after a combination, to an ionized cosmos, in which light could travel more freely through intergalactic space. That transformation, reionization, is often described in broad, almost atmospheric language, as though the universe simply brightened. But the process had to be driven by sources, harsh sources, compact hot stars, galaxies with intense radiation fields, feedback processes that did not merely decorate matter, but reorganize it. Reviews of JWST's first billion years results increasingly stress that the era is being rewritten in terms of unexpectedly rapid assembly, varied galaxy states, and more complicated internal physics than the older blurred picture allowed. So the problem with the blur is not only that it hid beauty, it hid consequences. That is why the old images of the distant universe could feel serene. Serenity is what unresolved light looks like. It is what violence looks like when it has been smeared over billions of light years and too few pixels. A dense star cluster in the epoch of Orionization may be one of the least serene things imaginable in physical terms. Ultraviolet radiation, winds, heating, feedback, eventual supernovae, and yet, from here, it can still arrive as a soft glint in the dark. We are very vulnerable to that illusion. Human beings are trained by ordinary scale. In daily life, small and faint often means weak. In cosmology, small and faint can mean catastrophically distant and locally ferocious. We are primates trying to infer the internal structure of the early universe from compressed light that has crossed most of cosmic history. Of course, we misread beginnings. Our nervous systems were not built for redshift. And this is where the Webb observation becomes psychologically sharper than it first appears. It is not just giving us more information about the early universe. It is removing one more layer of false comfort. It is taking a period that used to feel broad, dim, and vaguely formative, and forcing us to see that inside that dimness there were already compact, measurable concentrations of order, not the final universe, not mature in every sense, but no longer safely primitive either. That is the difference between a dawn seen from far away and a dawn seen up close. From far away, dawn is a gradient. Up close, it is ignition. And the more clearly we recover that ignition, the more the first billion years stop looking like a quiet beginning and start looking like a compressed era of selection, an interval in which some structures formed too densely, too efficiently, and perhaps too early for our old picture of cosmic adolescence. Which means we still have not reached the strangest part, because Webb did not achieve this alone. To see that far into the blur, the telescope needed an accomplice. Gravity had to bend the scene open. That is one of the least intuitive facts in astronomy, and one of the most beautiful. The telescope that helped reveal these clusters was not just Webb, it was Webb plus warped space-time. Webb provided the sensitivity, the infrared reach, the resolution. But between us and that galaxy, the universe had placed something else. A massive foreground galaxy cluster whose gravity distorted the path of light strongly enough to magnify the background system into a stretched arc now known as cosmic gems. In ordinary language, that sounds almost decorative. A distant object was magnified, helpful, useful, technically interesting. But the real meaning is harsher than that. Without gravitational lensing, some truths remain compressed beyond retrieval. The background galaxy is not merely far away, it is far enough, and small enough in apparent size, that its internal structure should have remained partly trapped inside distance itself. Light from its stars began travelling toward us when the universe was still in its first few 100 million years. On the way, it passed a massive cluster of galaxies whose gravity curved space-time and forced those rays into new trajectories. The result was not a simple brightening. Lensing stretched the image, magnified certain regions unevenly, and effectively turned the cosmos into its own optical system. Webb did not just look through space, it looked through gravity. That is an important distinction, because this is not the old fantasy of a telescope passively collecting whatever the universe offers. This is more intimate than that. The universe became part of the instrument. A foreground cluster, SPT-CLJ 0615-5746, acted as the lens. The distant galaxy behind it, at redshift about 10.2, was pulled into magnified arcs. Researchers could then model the lensing distortion, reconstruct the source plane structure, and estimate the intrinsic sizes and masses of the compact features embedded within the arc. What looked, from a more limited perspective, like one distant luminous form broke into multiple physically meaningful components. And here the psychological pressure deepens. Because lensing does not simply make the invisible visible, it reveals how much of reality was always there, hidden not by mystery but by scale. There is something almost cruel about that. The early universe did not wait for us to invent better telescopes before becoming complicated. Those compact clusters were already there, already dense, already radiating into their environment while Earth did not exist. while the solar system did not exist, while the Milky Way itself was still only one evolving structure among many. Their concealment was never about absence. It was about the fact that reality can be present long before it becomes legible. That is what makes lensing feel less like assistance and more like an act of exposure. We tend to imagine knowledge arriving because we advance toward it. Better theories, better instruments, better analysis. But in cases like this, knowledge also arrives because the universe briefly arranges itself in a way that lets hidden structure escape. The foreground mass, the background galaxy, the alignment, the magnification, the telescope, none of these alone would have been enough in quite the same way. What we call discovery is sometimes a negotiation between human precision and cosmic geometry. And when that negotiation works, it can be devastating for old intuitions. Because once you understand what lensing really did here, the emotional texture of the image changes. Cosmic gems stops being a pretty arc and becomes something more like a wound in smooth appearance. The graceful shape is not just beautiful, it is evidence that ordinary sight failed. It is evidence that the universe had to be optically broken open before its interior pressure could be read. That is why the arc matters. A normal unresolved galaxy from this era gives you a broad statement. There was light. There was star formation. Something had already assembled. A lensed, reconstructed galaxy gives you a narrower and more dangerous statement. There were locations inside that light where matter had already been forced into astonishing proximity. The distinction between those two statements is the distinction between early illumination and early structure. And structure is always the more consequential truth, because light can be misleading if you do not know its geometry. A soft glow tells you that energy exists. It does not tell you how tightly that energy is organized. A distant galaxy can look serene while hiding extreme local conditions. A stretched arc can look elegant while encoding something much more severe. Compact star-forming regions so intense that they begin to look like candidate ancestors of systems meant to endure for billions of years. That endurance matters. The paper's interpretation is careful, as it should be. These are candidate protoglobular clusters, not a cartoonishly final answer to every question about globular cluster origins. The responsible excitement comes from the combination of youth, compactness, and mass, along with the physical plausibility that such dense systems could be bound. In other words, we may not just be seeing some stars in an early galaxy. We may be seeing a class of object whose descendants could survive almost the entire age of the universe. And that possibility does something extraordinary to time. It collapses it. Instead of thinking in separated categories, early universe over here, ancient stellar relics over there, you're suddenly looking down one continuous line. The same story. Birth and fossilization connected by nothing except survival. A compact cluster forms in a chemically young galaxy less than 500 million years after the Big Bang, and under the right conditions, some version of that structure may persist through mergers, feedback, orbital stripping, galactic growth, and billions upon billions of years of dynamical history. A system like that is not merely old, it is transmissive. It carries conditions forward. This is one reason globular clusters have always felt slightly uncanny. In the nearby universe, they're among the oldest stellar systems we can study directly. Dense, ancient swarms hanging in galactic halos like relic organs from earlier epochs. They already looked like fossils. What Webb may be offering is the other end of the fossil record, not the relic after the fact, but the compact birth environment from which such relics could emerge. That does not close the case, but it sharpens it. Suddenly the idea is no longer purely theoretical or archaeological. It has light attached to it. Ancient light, freshly measured. And yet even this is only the surface of the implication. Because if gravitational lensing let us see these compact systems at all, then what it really exposed was not just their existence. It exposed our prior ignorance of how intense the internal life of the early galaxies may have been. That is the hidden violence inside improved resolution. Better sight does not merely decorate the same universe with more detail. Sometimes it changes the kind of universe you think you're looking at. A blurred beginning can feel broad and passive. A resolved beginning can feel compressed, strategic, almost selective. Certain regions form stars. Certain regions dominate feedback. Certain structures remain bound. Certain environments may disproportionately shape what the galaxy becomes. This is where the image stops being about magnification and starts being about leverage. Because a compact cluster is never only itself, not in a young galaxy, not in the epoch of Orionization. A dense concentration of young, massive stars does not sit quietly inside its host. It floods nearby gas with radiation. It injects momentum through winds. It raises temperature. It can alter whether additional stars form nearby or whether material is dispersed. In the right numbers, under the right conditions, such clusters become less like inhabitants of a galaxy and more like local engines inside it. Which means the lens did something more than enlarge a scene. It revealed pressure points. And once you start seeing pressure points instead of pretty light, the emotional register changes again. The early universe becomes less mist-like, less atmospheric, less romantic. It begins to feel engineered by density. Not engineered in the human sense, not designed, but sculpted by the brutal consequences of where matter happened to pile up hard enough, fast enough, for radiation and gravity to start arguing in public. That is the hidden gift of gravitational lensing. It does not just help us look back. It helps us stop lying to ourselves about what distance was doing to the truth. Because distance was not merely dimming the dawn. It was sanitizing it. The arc of cosmic gems is beautiful, but beauty here is almost a side effect. The deeper function of the lens was to strip away one layer of false gentleness, to take a galaxy from an era we like to imagine as formative and show that, inside that formative phase, there were already compact nodes of astonishing efficiency. Small on the sky, enormous in consequence. And now another threshold appears. Seeing the clusters is one thing. Understanding why their compactness changes everything is harder. Because once stars are packed that tightly, light is no longer just illumination. It becomes force. Not metaphorically, not poetically, physically. Once stars are packed into volumes this small, light stops behaving like a distant glow and starts behaving like pressure applied from within. Radiation is no longer something that simply escapes into space. It accumulates, interacts, and competes with gravity in a confined environment. The difference between stars exist and stars are compressed is the difference between illumination and influence. That is where these clusters cross a threshold. Because what Webb resolved inside that stretched arc were not loose populations. They were systems. 5 compact, young, massive clusters embedded within a region less than about 70 parsecs across, each only about a parsec in size, each holding on the order of 1 million solar masses in stars. That combination, small size, large mass, is not a gentle state of matter. It is a state under tension. To feel what that means, you have to let go of the distant framing. Forget the galaxy for a moment. Forget the redshift. Bring the scale closer in your mind until the numbers stop sounding abstract. A parsec is about 3 light years. Now imagine compressing 1 million suns into something only a few light years across. Not spread thinly, not drifting, bound, dense, gravitationally coherent. That is not a background glow. That is a localized event. And once you see it that way, the clusters stop feeling like decorations inside a galaxy and start feeling like nodes where physics intensifies. Gravity is already strong in a galaxy, but in a compact cluster it tightens further. Gas collapses more efficiently. Star formation becomes more synchronized. Massive stars appear in close proximity, and massive stars do not behave quietly. They burn hotter, die faster, and inject enormous amounts of energy into their surroundings. Radiation builds. Ultraviolet light floods outward, ionizing nearby hydrogen. Stellar winds, streams of charged particles push against surrounding gas. When the first of those massive stars end their lives, supernovae detonate into an environment that is already crowded, already heated, already unstable. The cluster becomes a pressure center. And pressure centers do not remain isolated in a young galaxy. They reshape their surroundings. This is where the observation stops being descriptive and starts becoming causal. Because a galaxy is not just a collection of stars. It is a dynamic system of gas, radiation, gravity, and feedback. Where stars form, how tightly they form, and how quickly they inject energy back into the system determines how that galaxy evolves. Loose star formation spreads its influence thinly. Compact star formation concentrates it. Concentration changes outcomes. If enough energy is released in a small enough region, it can clear gas, halt further star formation locally, or redirect material elsewhere. It can punch cavities into the interstellar medium. It can create channels through which radiation escapes more easily. It can destabilize nearby regions, or, in some cases, compress them further and trigger additional collapse. In other words, compact clusters are not passive results of galaxy formation. They are active participants in shaping it. That is why researchers emphasize that star cluster formation and feedback likely helped shape galaxies during the epoch of reionization. The clusters are not just something we observe, they are part of the machinery that determines what a young galaxy becomes. And that shifts the scale of the story again. Because once clusters are understood as engines, not just structures, the early universe stops being a place where galaxies slowly gather themselves into existence. It becomes a place where localized regions of extreme activity could disproportionately influence the evolution of entire systems. The first billion years begin to look less like a gradual emergence and more like a contest of efficiencies. Where did gas collapse fastest? Where did stars form most densely? Where did feedback become strong enough to reshape the environment? Where did structure become stable enough to survive? Those questions are not philosophical, they are physical, and compact clusters sit directly at their center. But there is another layer beneath this, and it is quieter. Because density does not only change how energy is released, it changes what survives. A loosely bound group of stars is fragile. Over time, interactions, tidal forces, and internal dynamics can disperse it. A tightly bound cluster, by contrast, has a different fate. Its gravity is strong enough to hold it together across long timescales, even as the galaxy around it evolves, merges, and transforms. That is where the idea of protoglobular clusters enters with real weight. Globular clusters in the nearby universe are among the oldest structures we can directly study. Dense, spherical collections of stars orbiting in galactic halos, many of them more than 10 billion years old. They already felt like relics, already felt like survivors. What Webb may be showing is not the relic after billions of years, but the birth environment that could produce such a relic in the first place. Not a memory, an origin. That does not mean every cluster we see will survive. It does not mean the connection is fully proven. The science remains careful, appropriately so. But the plausibility is no longer abstract. It is grounded in observation, compact, massive, young clusters existing at a time when the universe was still chemically primitive and dynamically intense. And that plausibility carries a deeper implication. If even a fraction of these clusters remain bound and persist, then some of the oldest structures we see today are not late refinements of cosmic history. They are direct transmissions from its earliest phases. Time, in that sense, does not erase everything. It preserves what is dense enough. That idea has a kind of quiet severity to it, because it suggests that the early universe was not only forming stars, it was already filtering them. Some structures would dissolve, some would disperse, some would be reprocessed into new generations of stars, and some, the densest, the most tightly bound, would endure, not unchanged, but continuous, carrying forward chemical signatures, dynamical properties, and structural memory from an era that otherwise feels unreachable. Survival becomes a selection process, and selection changes how we interpret beginnings. The first billion years are no longer just about what formed. They are about what formed in a way that could last. That shift matters because it pushes the story out of the comfortable frame of early development and into something more exacting. The young universe was not just building, it was already deciding, through physics alone, which of its creations would have futures. And the conditions that allowed that, low metallicity gas, high densities, rapid collapse, were not gentle conditions. They were efficient, sometimes extreme, and often unforgiving. The universe at that time had fewer heavy elements, which affects cooling and fragmentation, and it likely experienced rapid gas inflows and turbulent environments that favored intense, localized star formation. Chemically young, dynamically ruthless. That combination is not what we usually picture when we think of beginnings. But it may be closer to the truth, because what Webb has revealed is not just that structure appeared early, it is that the mechanisms capable of producing dense, long-lived structure were already in place. And once that becomes clear, a more unsettling question begins to take shape. If clusters this compact, this massive, this influential existed so early, then the early universe was not merely forming galaxies. It was already shaping their internal hierarchy. Not gently, not over long, forgiving timescales, but early, and in ways that concentrate consequence into very small regions. Because once star formation crosses the threshold into this kind of compactness, the question is no longer how many stars are being formed. The question is what those stars do to everything around them. 1 million suns spread across a galaxy will brighten it. 1 million suns compressed into a parsec will reorganize it. That is the difference Webb has forced into view. Inside these clusters, massive stars dominate the early energy budget. They burn hot, short, and intensely. Their radiation is not neutral light. It is ionizing light, energetic enough to strip electrons from hydrogen, to change the state of matter itself. In a diffuse environment, that radiation leaks outward gradually. In a compact cluster, it builds pressure first. Imagine standing inside a space where light does not just pass through, but accumulates, where photons are constantly being emitted into a region already filled with them, where energy density climbs, where the medium itself is being pushed, heated, destabilized. It does not stay contained, it breaks outward. Ultraviolet radiation floods into surrounding gas, carving ionized regions into what was previously neutral hydrogen. Stellar winds follow, streams of charged particles moving at enormous speeds, carrying momentum into the environment. Then, on timescales of only a few million years, the most massive stars begin to die. And they do not fade. They detonate. Supernovae in such environments are not isolated events. They occur inside regions already saturated with energy. Shockwaves collide with preheated gas. Turbulence intensifies. Material is pushed outward, compressed in some regions, evacuated in others. The cluster does not just exist inside the galaxy. It sculpts it. This is what feedback really means. Stripped of its technical calmness, it is the process by which star formation pushes back against the conditions that allowed it to happen. And when that process is concentrated, when it originates from a compact cluster instead of a diffuse population, its effects become disproportionately strong. That is why compression changes everything, because it turns star formation from a distributed phenomenon into a localized force, and localized forces create structure. In a young galaxy, that structure can determine where gas survives, where it collapses next, where it is expelled, and how the entire system evolves. It can influence whether the galaxy continues forming stars efficiently or begins to regulate itself. It can create channels through which radiation escapes more easily into intergalactic space. That last detail matters more than it first appears. Because the early universe was not just forming galaxies in isolation, it was undergoing a large-scale transformation, the transition from a mostly neutral state to an ionized one. This process, known as reionization, required enormous amounts of high-energy radiation, and that radiation had to come from somewhere. Not evenly, not passively, from concentrated sources capable of overwhelming their surroundings. Compact clusters are exactly that kind of source. They are small enough to be intense, and intense enough to matter beyond their size. If enough of them existed, and if their radiation could escape their host galaxies, they would not just illuminate the early universe. They would help change its fundamental state. They would contribute to the clearing of the cosmic fog, allowing light to travel more freely across vast distances. The dawn, in that sense, was not a gradual brightening. It was a series of localized burn-throughs, regions where radiation punched outward, ionizing hydrogen, expanding bubbles of transparency into a universe that had long been opaque. And those bubbles did not emerge from softness. They emerged from pressure. This is where the emotional tone of the story shifts again. Because once you understand the role of compact clusters in this context, the early universe stops feeling like a quiet beginning and starts feeling like a contested environment, one in which energy, matter, and geometry were already interacting in ways that produced winners and losers. Some regions collapsed efficiently. Some regions were disrupted. Some structures became stable. Some were erased. And the difference often came down to density. Density determines how strongly gravity binds matter. Density determines how intensely radiation accumulates. Density determines whether a structure can survive its own feedback. In other words, Density determines which parts of the early universe persist long enough to matter later. That is a much sharper picture than the one we usually carry. We tend to imagine beginnings as open-ended, as though everything that forms has a similar chance to continue. But in a universe governed by physical laws, beginnings are already selective. The conditions under which something forms constrain its future from the start. Compact clusters are an example of that constraint made visible. They are systems that formed under conditions strong enough to bind them tightly, and in doing so, they crossed a threshold. They became candidates for endurance. And endurance in cosmology is rare. Most structures are temporary. Gas clouds collapse and disperse. Star-forming regions flare and fade. Galaxies merge, distort, and rebuild. The universe is full of processes that create and destroy continuously. Stability is not the default state. It is something that must be earned through configuration. That is why the idea of protoglobular clusters carries such weight. If these compact clusters are indeed ancestors of the globular clusters we see today, then we are looking at systems that formed early and survived almost everything that followed. They endured galaxy mergers, tidal interactions, internal dynamical evolution, and billions of years of cosmic change. They are not just old. They are resilient, and resilience, in this context, is a direct consequence of how they formed. Tightly bound, high density, strong internal gravity, the same properties that made them intense in their youth are what may allow them to persist into deep time. That continuity collapses distance in a way that feels almost unnatural, because it means that something forming in a galaxy less than 500 million years after the Big Bang could, in principle, still exist in recognizable form today, not unchanged, but continuous. A thread pulled across nearly the entire history of the universe. That is not how we usually think about time. We think of the past as something that dissolves into the present, leaving only traces, but in some cases, the past does not dissolve. It condenses into structures that carry it forward, structures that act as archives, structures that preserve information about the conditions under which they formed, chemical composition, stellar populations, dynamical properties. Globular clusters, in this sense, are not just objects, they are records. And if Webb is showing us their possible beginnings, then we are no longer limited to reading the record backward. We are seeing the writing happen. That is a different kind of access. It does not give us certainty. It does not eliminate all ambiguity, but it changes the nature of the question. Instead of asking only how ancient clusters came to be, we can begin to observe environments where such formation is physically plausible and testable. And those environments are not calm. They are not gradual. They are not forgiving. They are efficient, concentrated, and in some cases, extreme, which leads to a deeper realization. The early universe was not just producing light. It was producing leverage, small regions with outsized influence, compact systems capable of reshaping their surroundings, structures dense enough to survive, and in surviving to carry the imprint of their birth conditions across cosmic time. And once you see that, the idea of the first billion years shifts again. It stops being a prelude. It starts looking like a phase where the universe was already deciding how it would look billions of years later. Not in detail, but in principle, through density, through compression, through the quiet, ruthless logic of which structures could hold themselves together long enough to matter. And that raises a harder question still. If density was already this decisive, then the early universe may not have been simple at all. It may have been selective from the beginning. Not in the sense of intention, not in the sense of design, but in the only way the universe ever selects anything, through the consequences of its own laws. Where matter collapsed faster, something different happened. Where it collapsed harder, something more permanent emerged. And that distinction begins to redraw the entire first billion years. Because once compact clusters enter the story as real, measurable systems, not theoretical possibilities, not statistical averages, but actual regions where density crossed a threshold, the early universe stops looking like a uniform phase of growth. It starts looking uneven, structured, biased towards certain outcomes. We often describe early galaxies as forming, as if they were gradually assembling themselves from diffuse material. But that language hides an important asymmetry. Formation is not smooth. It is lumpy, localized, and often dominated by regions that behave very differently from their surroundings. A galaxy is not built everywhere at once. It is built where conditions allow it to be built fastest. And compact clusters are what those fastest regions look like. They are the places where gravity wins quickly enough to pull gas into tight configurations before turbulence, radiation, or external processes can disperse it. They are the locations where star formation is not just happening, but happening efficiently enough to leave a lasting imprint. That efficiency is what makes them dangerous, in the best scientific sense of the word. Because efficient processes do not just add detail to a system, they control it. If most of the energy, most of the radiation, most of the feedback in a young galaxy is coming from a relatively small number of compact regions, then those regions act as regulators. They determine how the galaxy evolves, not by representing the average condition, but by dominating the extremes. And extremes are what shape systems. This is where the story begins to stretch beyond individual galaxies and into the wider universe again. Because if compact clusters are efficient sources of radiation, then they do not only affect their immediate surroundings, they contribute to something much larger, the gradual transformation of the intergalactic medium during reionization. But gradual is misleading. From a distance, reionization looks like a smooth transition. Neutral hydrogen becomes ionized over time. The universe becomes more transparent. Light travels more freely. It reads like a slow, global shift. Up close, it is anything but smooth. It is patchy, localized, driven by sources that do not act evenly across space. Regions around intense star formation become ionized first, forming bubbles of transparency that expand outward. Other regions remain neutral longer, waiting for radiation to reach them or for local sources to ignite. The process unfolds not as a uniform wash of light, but as an uneven expansion of influence. Compact clusters fit naturally into that picture. They are exactly the kind of sources that could drive such localized change, intense enough to ionize their surroundings, small enough to be numerous, and structured enough to potentially allow radiation to escape into intergalactic space. And escape is critical, because it is not enough for stars to produce radiation. That radiation has to leave the galaxy. It has to travel beyond the dense regions where it was generated, and into the wider cosmic medium. If it remains trapped, its influence is local. If it escapes, its influence becomes cosmic. Dense clusters, paradoxically, may help both conditions. Their internal intensity generates large amounts of ionizing light. Their feedback, winds, supernovae, turbulence, can disrupt surrounding gas, creating channels through which radiation can leak outward. In doing so, they turn local events into large-scale consequences. Small regions, large effects. That pattern repeats. And once you begin to see the early universe in those terms, the emotional landscape changes again. It becomes less like a quiet dawn and more like a field of emerging influence. Pockets of intensity expanding into surrounding darkness, competing, overlapping, and gradually reshaping the state of the entire cosmos. The darkness was not lifted all at once. It was eroded, burned through, region by region. That is a very different kind of beginning, because it means the early universe was not simply becoming visible. It was being actively transformed by the structures forming within it. And those structures were not neutral participants. They were biased toward efficiency, toward density, toward configurations that could generate and release energy effectively. Which brings us back to the idea of selection. Not everything that formed in the early universe mattered equally. Some regions were too diffuse to dominate. Some star formation was too spread out to have large-scale impact. Some structures were too fragile to persist. But others, compact, dense, efficient, were capable of shaping both their local environments and, through accumulated effect, the larger state of the universe. Those are the structures Webb is beginning to expose, not because they are the only things that existed, but because they are the ones that matter most for how the story unfolds. And that introduces a subtle but profound shift in how we interpret cosmic history. We tend to think of the universe as evolving in broad strokes, as though each era has a general character that applies everywhere. But the more closely we look, the more that illusion breaks down. Reality is not governed by averages, it is governed by extremes. The average region of a young galaxy might have been relatively quiet, but the extreme regions, the compact clusters, are where the decisive processes occurred. That is where gas was most strongly processed. That is where radiation was most intense. That is where feedback was most disruptive. That is where survival became possible. And those extremes do not just exist alongside the rest of the system. They define it. This is why the early universe, once resolved, begins to feel less like a gentle beginning and more like a phase of concentrated decision-making, not conscious, not directed, but encoded in physics. Certain configurations of matter lead to certain outcomes, certain densities lead to certain futures, and once those configurations appear, they set constraints that ripple forward through time. A compact cluster that survives becomes part of a galaxy's long-term structure. A region that clears gas alters where future stars can form. A source that contributes to rionization changes the transparency of space for everything that follows. These are not isolated effects. They accumulate. They interact. They build a trajectory. Which means the first billion years were not just about what existed. They were about what began to matter. And what began to matter, increasingly, were the regions where the universe managed to compress itself into something capable of acting back on its environment. That is the deeper implication of these observations. Not just that the early universe had structure, but that it had leverage. And leverage changes how systems evolve. It means small differences can produce large outcomes. It means certain regions can dominate the future of much larger systems. It means beginnings are not neutral starting points. They are already tilted toward density, tilted toward efficiency, tilted toward the kinds of structures that can both survive and reshape everything around them. And once you accept that, the idea of a primitive universe becomes harder to hold on to. Because primitive suggests simplicity. It suggests a lack of differentiation. It suggests a state before things begin to matter in complicated ways. But what Webb is showing is that complication was already there. Not everywhere, but in the places that counted. Which leaves us with a more unsettling picture. The early universe was not a blank stage waiting for the main act. It was already full of actors powerful enough to influence the script. And those actors were small, dense, and in their own way, decisive. Which raises the next layer of the question. If the early universe was already this uneven, already shaped by concentrated regions of influence, then how much of what we see today is not the result of slow evolution, but the echo of those early imbalances? That possibility is harder to sit with than it first sounds, because we like to imagine the modern universe as something that emerged gradually from broad statistical trends: dark matter, halos growing, gas cooling, galaxies merging, stars enriching the cosmos over time. All of that is true, but it is not the whole truth. Large histories are often steered by smaller symmetries that appear early and then refuse to disappear. A slight advantage in density here, a stronger collapse there, a compact cluster that survives where other structures dissolve. Over billions of years, those differences do not simply remain local, they accumulate into architecture. This is where the story of these clusters begins to turn into something more haunting than an observation. Because if they really are protoglobular clusters, or even if they are close relatives formed under similar conditions, then Webb is not merely showing us intense star formation in the young universe. It is showing us the birth environment of some of the oldest long-lived stellar systems we know. The nature result explicitly argues that the compact sources in cosmic gems are consistent with bound stellar systems and candidate protoglobular clusters. That phrase matters: bound stellar systems. Bound means gravity won decisively enough to keep the structure together. And keeping something together in the early universe was no small achievement. The first billion years were not a calm nursery. They were dynamically violent. Gas was flowing, collapsing, heating, fragmenting, being ionized, being expelled. Galaxies were assembling quickly. Radiation fields were intense. Heavy elements were still scarce compared with later cosmic epochs. And JWST-era reviews increasingly frame the first billion years as a period of rapid assembly and unexpectedly mature internal structure rather than a simple, primitive prelude. So if a cluster formed under those conditions and remained bound, that alone says something severe about its internal configuration. It says the density was not incidental. It was sufficient to cross from temporary brightness into structural endurance. That is a profound distinction, because most events in the universe are local and temporary. They happen, radiate, disperse, and vanish into larger histories. A star-forming region can be brilliant and still leave almost nothing stable behind. But a bound cluster is different. It carries itself forward. It enters time as an object, not just an episode. And objects that endure become archives. That is why globular clusters have always felt so strange in the nearby universe. They orbit galaxies like sealed containers from another age, dense, ancient swarms of stars that often predate much of the galactic structure around them. In the Milky Way and other galaxies, globular clusters are among the oldest directly observable stellar systems, and astronomers have long treated them as fossils of early formation environments. The Webb result sharpens that old intuition by giving us a plausible look at such systems near birth, rather than only after 13 billion years of survival. That changes the emotional geometry of the story. Until now, the script has been moving outward, from blurred light to resolved clusters, from clusters to feedback, from feedback to galaxy shaping, from galaxy shaping to rionization. But here time folds instead of expands. Suddenly the path is not only outward into consequence, it is forward across epochs. A dense cluster forms in a chemically young galaxy less than 500 million years after the Big Bang. The galaxy evolves, it merges, it is torn at, it accretes, it loses gas, it gains stars, its shape changes, its environment changes. And still, under the right conditions, the cluster remains. Not untouched, not frozen, but continuous. A knot of early universe matter holding itself together while almost everything around it is revised. That is what survival means at cosmic scale, not immortality, persistence through revision. And that persistence has consequences for knowledge. Because if some present-day globular clusters really are descendants of systems like the ones Webb is now glimpsing, then the oldest stellar fossils in nearby galaxies are not just relics we study backward. They become endpoints of a line that JWST has begun to illuminate from the other side. One end is local and ancient, the other is remote and young. Between them lies almost the full age of the universe. That line is scientifically powerful because it links observation across deep time, but it is also psychologically destabilizing. It means that in at least some cases, the past is not gone in the way we usually mean by gone. It has survived in compressed form. That is a pattern the universe seems to favor. Diffuse things mix, merge, blur, and disappear into averages. Dense things resist. Dense things keep their identity longer. Dense things transmit their conditions forward. What Webb may be showing is not just that the early universe formed stars quickly, but that it formed some structures in a way that allowed them to become carriers of memory. And memory, in physics, is always expensive. It requires stability against noise. It requires binding against disruption. It requires a configuration that can endure collisions with history. That is why density matters again here, but in a deeper register than before. Earlier, density meant pressure, intensity, feedback. Now density means continuity. The same compactness that made these clusters locally ferocious may also be what allows them to outlast the era that made them. Compression is not just destiny inside a galaxy, it is destiny across time. This is the midpoint where the subject quietly changes. At first, the clusters seem like an answer to a technical question. How early could dense star formation happen? Now they become an answer to a harder one. How early could the universe begin producing survivors? That is a much sharper question, because survival is where beginnings stop being about activity and start being about inheritance. Plenty of things can flare into existence. Far fewer can carry any part of their origin across billions of years. And the possibility that the cosmic dawn was already producing inheritances so early should change the emotional weight of that era. We usually picture dawn as transition, a state between darkness and clarity, between absence and presence. But if some of the structures formed during that dawn are still with us in evolved form, then dawn was not merely transition. It was already legacy. That word lands differently when you remember the timescale. These candidate clusters are seen at about 460 million years after the Big Bang. That is not late in cosmic history. That is almost at the beginning of galaxy formation as we can directly observe it. And already, perhaps, reality is producing systems dense enough to become long-term inhabitants of the universe rather than short-lived outbursts. The emotional effect of that should not be simple or is too smooth. The better feeling is something colder, because this tells us that the universe did not need long to start selecting what would remain. That is the deeper correction Webb is forcing onto us. We think of beginnings as broad opportunities, open possibilities, unfinished states. But the young cosmos may have been much more discriminating than that. Certain conditions produce structures that would vanish. Other conditions produce structures that would persist almost indefinitely. The difference was not philosophical, it was physical. How tightly did gravity bind the stars? How strongly did feedback disrupt the gas? How much mass was gathered into how little space? Could the system hold itself together against everything that came next? These are ruthless questions. The universe answered them without ceremony. And now, for the first time, we may be watching some of those answers emerge in real data. That is why this moment is more than a beautiful result. Beautiful results happen all the time in astronomy. What makes this one more dangerous is the way it compresses origin and fossil into the same frame of thought. You're no longer looking only at a remote galaxy. You're looking at the possible early phase of a class of objects that may still populate galactic halos today. Ancient light, future relics. The phrase sounds poetic, but here it is almost literal. Webb may be showing us systems before they became ancient. And once you let that settle, the first billion years become harder to describe as merely formative. Formative suggests a stage before the important things are fixed. But some important things may already have been fixed here. Not every detail, not every later structure, but the existence of bound stellar systems dense enough to survive and influential enough to shape their environments. That is a second ignition for the whole script. Because the real shock is not only that the early universe formed stars fast, it is that it may already have formed survivors. And survivors carry power far beyond their size. They preserve chemical signatures, they preserve dynamical memory, they anchor models of how star formation worked under early conditions. They let us test whether the old fossils around nearby galaxies are truly connected to the compact engines Webb now sees at the edge of observability. The first billion years, seen this way, stop looking like a dim preface and start looking like a brutal filtration process. Some structures were born bright and vanished. Some were born diffuse and mixed into later histories. Some were born dense enough to endure. And the ones that endured may still be teaching us what the dawn was really like. Which leads to the next pressure point. If survival this early was even possible, then the young universe was not only making light, it was already making history. Not the kind we write down, not events arranged in sequence, but structures that carry their origin forward, physical records that persist, not because they were meant to, but because they were built in a way that allowed them to. That changes what early means. We tend to treat the beginning of things as disposable, as though whatever happens first is inevitably overwritten by what comes later. In everyday experience, that is often true. Early forms are rough. They get refined, replaced, erased. But in the universe, erasure is not guaranteed. If something forms under the right conditions, dense enough, bound enough, stable enough, it can outlast almost everything around it. And that possibility reframes the clusters completely. They are no longer just intense regions inside a young galaxy. They are candidates for continuity. To understand why that matters, you have to feel the difference between two kinds of existence. There is the kind that flares, brief, bright, influential in the moment, but ultimately dissolving into the larger system. And there is the kind that holds, that maintains identity across change, that resists mixing, that persists through environments that are constantly trying to reshape it. Most of the early universe belonged to the first category. Gas collapsed, formed stars, heated, dispersed. Galaxies grew, merged, restructured. Radiation flooded regions and then moved on. Almost everything was in motion, and most of it did not keep its original form. But dense, bound clusters sit in the second category. They do not ignore change, they endure it. And endurance has consequences that ripple far beyond the object itself. Because anything that persists becomes a reference point. It anchors processes around it. It carries information forward. It allows later observers, like us, to infer conditions that would otherwise be inaccessible. A surviving cluster is not just a remnant. It is a constraint on history. It tells you something about the environment that produced it, simply because that environment had to be capable of creating something that could last. That is why the idea of protoglobular clusters is so powerful here. Globular clusters in the present-day universe are ancient, dense, and remarkably uniform in certain ways. They have long been used to probe the early conditions of galaxy formation, but until now, they have mostly been studied as fossils, as endpoints. Their origins were reconstructed indirectly, through modelling, through chemical signatures, through inference. What Webb may be offering is a glimpse of the beginning of that same lineage. Not the full story, not every detail, but a direct observation of environments where such structures can plausibly form. That shortens the distance between cause and evidence. It turns a long-standing question, how did globular clusters form, into something closer to an observable process. The clusters in cosmic gems are not yet proven ancestors, but they exist in the right regime, compact, massive, young, and embedded in a galaxy from a time when the universe was still chemically primitive. That alignment is enough to shift the burden of imagination. We no longer have to guess what such formation might have looked like in general terms. We can begin to see what it looks like in at least one real case, and what it looks like is not diffuse, not tentative, not gradual in the way intuition prefers. It is concentrated. That concentration is the thread connecting everything so far. It explains the intensity of feedback. It explains the ability to shape a host galaxy. It explains the potential contribution to rionization. And now it explains the possibility of survival. The same physical condition, matter compressed into a small enough volume, creates both immediate influence and long-term endurance. That dual role is what makes these clusters so central to the story. They are not just events, they are pivots, points where the behavior of the system changes. And once you recognize that, the early universe begins to feel less like a uniform field and more like a landscape of pivots, regions where conditions crossed thresholds and, in doing so, altered the trajectory of everything around them. Some of those pivots were weak. They formed, influenced their surroundings briefly, and disappeared into later evolution. Others were strong. They formed under conditions that allowed them to persist, to continue interacting with their environment, to remain as discrete entities across time. The difference between weak and strong pivots is not philosophical. It is structural. How much mass, how much compression, how much binding energy, how resilient against disruption? Those are the questions that decide which parts of the early universe leave a lasting mark. And this is where the midpoint realization deepens. The real shock is not that the early universe contained activity. It is that it contained stability. Even if only in certain places, under certain conditions, that stability is enough to change how we think about cosmic beginnings. Because stability introduces memory. It allows the universe to carry forward specific configurations instead of constantly resetting them. Without that, history would be smooth. With it, history becomes layered. You can have objects that originated in one epoch and still exist, in evolved form, in another. You can have structures that act as bridges between eras, linking conditions that would otherwise feel disconnected. You can, in principle, trace a line from the first few 100 million years to the present day, not through abstract models, but through actual physical systems that survived the journey. That is a very different kind of continuity, and it introduces a new kind of tension into the story, because if the early universe was already capable of producing stable, long-lived structures, then the boundary between early and late becomes less clear. The dawn is no longer just the moment before complexity. It is part of the same continuum that leads to everything we see now. The difference is not that complexity suddenly appears later. It is that we become able to see it. That is an uncomfortable idea. It suggests that the simplicity we associate with beginnings is, at least in part, an artifact of limited resolution, a result of distance, of faintness, of observational constraints. As those constraints fall away, the early universe reveals itself not as a smooth gradient into complexity, but as a system that already contained pockets of intense organization, pockets that mattered, pockets that lasted. And those pockets were not large. They were small, dense, and easily lost in the blur, which brings the entire narrative back to a single inversion. What looks small from here is not necessarily small in consequence. The clusters in cosmic gems are tiny on the sky. Without lensing, they might not have been resolved at all. Even with Webb, they sit at the edge of what can be measured. They are visually insignificant in the grand scale of the cosmos. And yet, they may represent one of the most consequential modes of structure formation in the early universe. That mismatch between appearance and importance is the real fracture in intuition. We are trained to associate scale with significance. Large things matter. Small things are details. But the early universe does not follow that rule. In many cases, the structures that dominate the evolution of a system are not the largest ones. They are the densest ones. Density concentrates influence. Density creates leverage. Density allows survival. And once you accept that, the hierarchy of importance shifts. Galaxies are still vast. Cosmic structures are still enormous. But inside them, it is often the compact regions, the clusters, the dense cores, the localized engines that determine how the larger system behaves. That is the hierarchy the early universe may have established very quickly. Not a flat distribution of influence, but a layered one. Diffuse regions providing mass and context, dense regions providing action, and the balance between those layers shaping everything that follows, which leads to the next escalation. If compact clusters were not just present, but central, if they acted as pivots, as engines, as survivors, then the early universe was not just uneven. It was already organizing itself around these concentrations. And that raises a harder, more structural question. Not just how galaxies formed, but how their internal architecture was decided so early. That is where the subject deepens again. Up to now, the clusters have looked like remarkable objects inside young galaxies, compact, massive, intense, and perhaps long-lived. But that still leaves a subtler question unresolved. Why these objects? Why this level of compression, this early? What was different about the young universe that made such concentrated formation possible at all? Because if our old intuition was wrong, it was wrong in a very specific way. We did not merely underestimate how soon stars could form. We underestimated how soon matter could organize itself into structures dense enough to become both powerful and durable. And that mistake begins with chemistry. The first billion years were not chemically rich. Heavy elements were still scarce compared with later cosmic history. Carbon, oxygen, iron, silicon, the ingredients forged and dispersed by generations of stars, had not yet had much time to accumulate. The gas inside early galaxies was, by later standards, relatively metal-poor. That fact matters because metals change how gas cools, fragments, and forms stars. In the nearby universe, metal-enriched gas can radiate energy away more efficiently in certain regimes and fragment into complex structures across a wide range of scales. In the early universe, the pathways were different, the conditions harsher, and the balance between cooling, collapse, turbulence, and feedback more severe. Reviews of JWST's first billion years results increasingly emphasize that young galaxies appear highly diverse, rapidly assembled, and physically more extreme than the older, smoother picture suggested. That is the first correction. The young universe was chemically poor, but dynamically ruthless. It had fewer ingredients, but not less intensity. Gas was flowing into dark matter halos. Gravity was gathering matter quickly. Local densities could rise fast. Star formation did not happen in a calm laboratory after perfect preparation. It happened inside a system still building itself, where inflow, collapse, radiation, and disruption were all competing almost at once. That matters because structure does not emerge only from abundance. Sometimes it emerges from pressure. A later, more enriched universe has more ways to form stars. An earlier universe may, in some places, have had stronger reasons to form them violently. This is one of the hardest adjustments for human intuition, because we tend to confuse primitiveness with weakness. We hear chemically young and imagine underdeveloped. We hear early galaxy and imagine something broad, vague, and unfinished. But the absence of later complexity does not imply the absence of extreme local conditions. In fact, it may do the opposite. Less settled systems can be more unstable. More unstable systems can collapse more abruptly. And abrupt collapse is exactly the sort of thing that creates compact star-forming regions rather than gentle stellar distributions. The universe, in other words, did not need maturity to become dangerous. It only needed gravity, gas, and enough asymmetry for some regions to fall inward faster than others. That is where internal architecture begins. A galaxy is not born with one uniform character. It is born with gradients, differences in density, differences in inflow, differences in angular momentum, differences in how gas fragments and where it can remain compressed long enough to turn into stars before feedback tears it apart. Once those differences appear, the galaxy is no longer a blank system. It starts acquiring internal hierarchy. Some regions become dominant because they are denser. Some become dominant because they form stars earlier. Some become dominant because they survive their own violence. And once a compact cluster forms, it is not just another part of the galaxy. It becomes a local authority inside it. That is the deeper meaning of density. Density is not only a number, it is a ranking mechanism. It determines which regions of a galaxy get to matter most. A diffuse stellar population contributes light. A compact cluster contributes decisions. Not conscious decisions, of course. Physical ones. It determines where gas is heated, where ionization spreads first, where feedback becomes concentrated enough to reshape the surrounding medium. The cluster's existence changes the future options available to the galaxy around it. This is why the Webb observation feels larger than the scale of the objects themselves. It is not merely that these clusters are early. It is that they reveal a galaxy whose interior was already differentiating into high-consequence and low-consequence regions. That is architecture, not the visible shape of the galaxy as a whole, but the deeper arrangement of influence inside it. This is also why the old picture of early galaxies as simple building blocks now feels too gentle. A building block is passive. It waits to be combined into something larger. But galaxies in the first billion years were not passive units waiting for cosmic assembly. They were already internally active systems, with localized engines, gradients of power, and regions capable of driving much of the system's evolution from within. The real shock is not that galaxies existed this early. It is that some of them already had interior politics. That phrase is metaphorical, but the physics beneath it is not. Not every region inside a galaxy matters equally. Some dominate the radiation field, some dominate feedback, some dominate survival. Once compact clusters emerge, the galaxy is no longer just forming stars. It is sorting itself into zones of consequence. And this is where the first billion years stop looking primitive in a more radical sense. Primitive suggests flatness. Primitive suggests low differentiation. Primitive suggests a reality not yet capable of layering itself internally. But Webb is showing the opposite. Even in this youth, even under chemically sparse conditions, some galaxies were already capable of generating compact stellar systems that may shape their hosts, influence rionization, and potentially survive into deep cosmic time. That is not flat. That is stratified. Stratified systems are harder to predict, because once internal hierarchy appears, averages become less useful. The average gas density of a galaxy tells you less than the density in the handful of regions where everything important is happening. The average radiation field tells you less than the compact sources punching holes through local gas. The average history of the galaxy tells you less than the fate of the structures that remain bound. This is another place where human intuition fails. We like smooth stories because smooth stories are cognitively cheap. The universe prefers threshold behavior. Nothing seems to happen. Then suddenly a region crosses a critical density and its role changes. A cloud becomes a cluster. A source becomes dominant. A local event becomes a system-level force. That is how internal architecture is built. Not all at once, not by design, but by thresholds crossed earlier than we expected. And once those thresholds are crossed, the galaxy begins to acquire memory. Not just through long-lived objects, but through rearranged conditions. Gas removed here cannot form stars there. Radiation escaping from one compact region changes what remains neutral beyond it. A bound cluster that survives becomes part of the galaxy's future gravitational structure. Earlier symmetries stop being temporary. They begin to harden into history. This is the midpoint where the scale of the question changes again. The subject is no longer merely whether the early universe formed impressive clusters. The subject is whether those clusters were one of the ways the early universe began locking in its later form. That is a more unsettling thought, because it implies that some portion of cosmic history was not a slow drift toward complexity, but a rapid establishment of leverage points. Dense regions formed early, acted early, survived early, and in doing so helped determine which futures remained available. The beginning was not neutral. It was already selecting trajectories. And if that is true, then the 5 compact lights inside cosmic gems are not just a technical triumph or a beautiful observation. They are evidence that the early universe was already building internal hierarchies strong enough to matter across scales, from parsec-sized clusters to galaxy-scale feedback to universe-scale ionization and, possibly, to the fossil record of globular clusters we still see today. Small on the sky, decisive in the system. That is the pattern now, and once you recognize it, the dawn becomes harder to describe as a beginning in the innocent sense. It starts to feel like a sorting phase, a time when matter was already being forced into unequal roles, some temporary, some dominant, some durable enough to carry the imprint of that era forward, which leads directly into the next rupture. Because if compact clusters were helping decide the internal architecture of early galaxies, then their importance was not confined to the galaxies themselves. Their light was spilling outward. Their influence was beginning to leak into the universe at large. Their light was spilling outward, not as a gentle glow, but as something more invasive. Radiation with enough energy to change the state of matter beyond the boundaries of the galaxies that produced it. This is where the scale breaks open. Up to now, the clusters have shaped their host galaxies. They have acted as local engines, compressing, heating, clearing, stabilizing, or disrupting the material around them. But once their radiation escapes, they stop being local. They become cosmological, because the early universe was not transparent. After recombination, hydrogen filled space in a mostly neutral state. Light could not travel freely through it at all energies. High-energy photons, especially ultraviolet, were absorbed, scattered, trapped. The universe, in that sense, was not just dark, it was opaque in a very specific way. Reionization is the name we give to the process that changed that. But the word is too smooth for what actually happened. Reionization was not a uniform transition, like a dimmer switch slowly increasing brightness across the entire cosmos. It was a fractured process, uneven, patchy, driven by sources that ignited at different times, in different places, with different intensities. And those sources had to do something very specific. They had to overwhelm hydrogen, not everywhere at once, but locally, repeatedly, persistently, until those local changes overlapped and began to connect. This is where compact clusters enter the story with full force. Because if you ask what kind of object is capable of producing large amounts of ionizing radiation in a small volume, and doing so early, and doing so in a way that might allow that radiation to escape into intergalactic space, you arrive here, young, massive, tightly bound clusters filled with hot, short-lived stars. These are not quiet objects. Their stellar populations are dominated by massive stars that burn at extreme temperatures, producing intense ultraviolet light. In isolation, a single star can ionize its immediate surroundings. In a dense cluster, thousands or millions of such stars act together. Their radiation fields overlap. Their influence compounds. The result is not just illumination. It is transformation. Inside the galaxy, this radiation carves out ionized regions, heating gas and changing how it can collapse. But if pathways open, if feedback processes disrupt enough surrounding material, some fraction of that radiation can escape the galaxy entirely. And once it escapes, it does not stop. It moves outward into the intergalactic medium, encountering neutral hydrogen and ionizing it. Each cluster becomes a seed of transparency, a localized region where the universe is no longer opaque to certain wavelengths of light. Now imagine not one cluster, not one galaxy, but many, scattered across the early universe, igniting at slightly different times, under slightly different conditions, each producing its own expanding region of ionization. At first, these regions are isolated, islands of altered physics in a sea of neutrality. But they grow. They expand outward, driven by continuous radiation from their sources. Eventually, they begin to overlap. One bubble meets another, boundaries dissolve, the universe, region by region, transitions from neutral to ionized. Not smoothly, but through contact. That is what ionization really looks like when you strip away the abstraction. It is not a background change. It is a network of expanding influence zones, driven by localized engines. And compact clusters are exactly the kind of engine that fits that description. They are small enough to be numerous, intense enough to matter, structured enough to create escape pathways, and early enough to participate in the initial phases of this transformation. This does not mean they are the only contributors. Galaxies as a whole, populations of stars, and other sources all play roles. The science remains careful on this point. Ionization is a collective process, not the work of a single class of object. But what Webb has done is shift the plausibility landscape. Before, we knew that early galaxies must have contributed. Now we are beginning to see the kinds of internal structures that could have made that contribution more efficient than we expected. That matters because efficiency changes timelines. If radiation is produced and escapes more effectively than assumed, then the pace of ionization can accelerate. The transition from opaque to transparent can occur differently than older models predicted. The spatial structure of that transition, where ionization happens first, how bubbles grow, how they overlap, can also shift. In other words, these clusters do not just add detail to an existing picture. They apply pressure to it. They force us to reconsider how quickly, how unevenly, and through what mechanisms the early universe changed its own optical state. And that brings us back to the deeper pattern. Small regions, large effects. A parsec-scale cluster influencing tens or hundreds of parsecs within a galaxy. Multiple clusters influencing the structure of that galaxy. Many such galaxies contributing to ionization across vast regions of intergalactic space. The scale multiplies, but the logic remains the same. Density creates leverage. Leverage creates reach. Reach creates transformation. This is the moment where the early universe stops feeling like a collection of separate systems and starts feeling like an interconnected field of influence. Local processes do not stay local. They propagate, they accumulate, they interact. And the agents of that propagation are not the largest structures. They are the most efficient ones. That inversion is now complete. The clusters, once seen as small details inside distant galaxies, become central actors in a universe-wide transition. Their importance is not in their size, but in their ability to concentrate energy and release it in ways that extend beyond their immediate environment. They are pressure points in a much larger system. And once you see the early universe as a network of pressure points instead of a uniform expanse, its character changes again. It becomes less like a smooth dawn and more like a field of ignition sites. Each site carving out its own domain of influence. Each domain expanding until it meets others. Each interaction contributing to a larger transformation that no single region controls. The darkness was not lifted by a single light. It was broken apart by many, and those breaks began in places like this. Compact, dense clusters forming inside young galaxies, releasing energy in ways that could not be contained. That is the external consequence of what Webb has revealed. But there is still an internal one. Because once you accept that the early universe was shaped by these concentrated sources of influence, that its transformation depended on localized extremes rather than uniform conditions, then something deeper begins to unravel. Not just our picture of the cosmos, our intuition about how reality organizes itself. Because what this suggests is not only that the early universe was uneven, it suggests that unevenness is the rule, not the exception. That what looks smooth from a distance is often structured underneath. That what appears gradual may be driven by thresholds crossed in hidden places. That what feels like a general process may actually be the sum of many local imbalances. And that realization does not stay confined to cosmology. It reaches back into the way we interpret any large system. We look for averages because averages are easy to think about. But the universe seems to prefer extremes. The average region of space may have been quiet, but the regions that mattered were not average. They were dense. They were intense. They were decisive. And they appeared earlier than we expected. Which leaves us with a final, uncomfortable correction. The early universe was not simply becoming visible. It was already being shaped by the same kind of hidden asymmetries that still govern it today. That is the part that does not stay comfortably inside astronomy. Because once you follow the logic all the way through, the subject stops being early star clusters and becomes something more unsettling. The possibility that reality, at every scale, is less driven by smooth averages than by concentrated imbalances that appear early and refuse to disappear. We prefer averages because they feel stable. The average temperature of a region, the average density of a galaxy, the average behavior of matter. Averages are easy to describe, easy to model, easy to imagine. They create the illusion that systems evolve in a kind of calm, statistical flow. But the universe does not evolve through averages. It evolves through thresholds. Nothing happens for a long time, and then somewhere, a condition is crossed. Density increases just enough. Cooling becomes just efficient enough. Collapse becomes just fast enough. And suddenly, a region changes its role entirely. A gas cloud becomes a star-forming region. A star-forming region becomes a compact cluster. A compact cluster becomes a source of feedback strong enough to reshape its galaxy. A galaxy becomes a contributor to reionization. The scale expands, but the trigger is always local. That is the deeper pattern Webb is exposing. Not just that the early universe had structure, but that it had early thresholds, moments where matter crossed into regimes that carried disproportionate consequences. And once a threshold is crossed, the system does not return to neutrality. It carries the change forward. This is why the idea of primitive beginnings becomes harder to defend. Primitive suggests a lack of differentiation, a kind of uniform starting point from which complexity gradually emerges. But what Webb is showing is that differentiation may have been present almost immediately, not everywhere, but in the places that mattered most. The early universe was not smooth and then structured. It was structured in pockets from the start. And those pockets did not just coexist with the rest of the system, they dominated it. This is where the psychological tension sharpens into something more philosophical. Because it suggests that our intuition about how reality builds itself is fundamentally miscalibrated. We expect complexity to be late. We expect influence to scale with size. We expect beginnings to be simple. But the universe seems to prefer something else. Complexity can appear. Early influence can come from the small beginnings can already contain hierarchy. That inversion is not just about astronomy. It is about how we think. We are used to environments where small things are negligible, where early stages are incomplete, where systems only become decisive after long development. That intuition works at human scale. It fails at cosmic scale. And Webb is now precise enough to show us where it fails. Those 5 compact clusters are not anomalies in the sense of being rare curiosities. They are anomalies in the sense of breaking a mental model. They reveal that what we thought of as a broad, diffuse phase of cosmic history already contained highly organized, high-consequence structures. They expose the gap between appearance and mechanism. From a distance, the early universe looked like a gradient. Up close, it looks like a field of thresholds. And thresholds are where reality changes its rules. This is also why the discovery feels destabilizing in a quiet way. There is no explosion, no single dramatic event, no catastrophic headline, just a refinement of resolution, and suddenly the story underneath shifts. That is how most real corrections to our understanding happen, not through spectacle, through clarity, and clarity often removes comfort, because the older picture, the gentle dawn, the slow assembly, the gradual emergence of complexity, was easier to hold. It aligned with intuition. It aligned with the idea that time is what builds structure. The newer picture is colder. Time still matters, but it is not the only driver. Conditions matter, density matters, local asymmetries matter, and when those factors align early, they can produce structures that act, influence, and endure far sooner than we expect. Which means the universe does not wait for time to organize it. It organizes itself wherever the conditions allow. That is a very different kind of order. It is not sequential. It is opportunistic. Wherever matter can collapse, it does. Wherever energy can concentrate, it does. Wherever a structure can become stable, it does. And once it does, it begins to shape everything around it. This is the same logic that runs through the entire script, now exposed in its simplest form. Small regions, high density, early thresholds, large consequences, survival, propagation, transformation. That chain does not begin late. It begins as soon as it can. And that is what Webb has made difficult to ignore. Because once you see compact clusters forming this early, already dense, already influential, already potentially long-lived, you can no longer imagine the early universe as waiting to become what it is. It was already becoming it, already making decisions in the only way physics can, already creating differences that would not be erased, already establishing patterns that would echo forward across billions of years. This is where the opening image begins to change its meaning. At the start, those 5 points of light felt improbable. Now they feel inevitable, not because we expected them, but because once the underlying rules are visible, something like them had to exist somewhere. And once they exist, they cannot be contained. They shape their galaxies. They contribute to ionization. They may survive as relics. They carry information forward. They turn the early universe into a place where cause and consequence are already tightly linked. Which leaves one final correction. The most difficult one, because it is not about stars. It is about how we see reality itself. We look at distant systems and assume that what appears smooth is truly simple. We look at early stages and assume they are incomplete. We look at faintness and assume weakness. But the universe does not obey those associations. Smoothness can hide structure. Early does not mean undeveloped. Faint does not mean insignificant. And once you accept that, something shifts. You stop trusting the surface. You start asking where the density is, where the thresholds are, where the leverage points are hidden. And that is the real transformation this observation creates. Not a new fact, a new way of seeing. Because the next time you look at a distant galaxy, a faint arc, a small smear, a barely resolved point of ancient light, you're no longer looking at something simple. You're looking at something compressed, something whose internal structure may already contain the kinds of asymmetries, thresholds, and concentrated regions of influence that decide how systems evolve. Something that, even at the beginning, was already carrying the logic of everything that would follow. And that realization does not resolve the universe. It makes it harder. Because now the question is no longer how complexity emerges over time. The question is how early reality becomes complex enough to matter. And by now, the answer is no longer comfortably late. Not after Webb, not after lensing, not after those compact clusters and cosmic gems forced the issue. A galaxy seen at redshift about 10.2, only around 460 million years after the Big Bang, contains 5 compact sources consistent with young massive star clusters, each extraordinarily dense by any intuitive standard and physically plausible as candidate protoglobular clusters. The observation itself is narrow. Its implication is not. Because once the beginning contains structures like that, the beginning is no longer merely a beginning. It is already a selection environment. That is the quiet revelation everything has been converging toward. The first billion years were not just a period in which matter happened to exist before the real universe emerged. They were a phase in which reality was already sorting itself, deciding through nothing but law and condition, which regions would become luminous, which would become influential, which would remain bound, and which would vanish into later averages. Some gas collapsed and stayed coherent, some collapsed and tore itself apart. Some regions became sources, some remained background, some structures were transient, some became inheritances. That is not a soft dawn, that is filtration. And the word matters, because filtration is harsher than formation. Formation suggests open possibility. Filtration suggests pressure, thresholds, exclusion. It suggests that from the beginning, not everything had the same chance to matter. That is what density has really meant all along in this story. Not just compactness, not just intensity, not just brightness. Priority. Dense regions get to act first. Dense regions get to shape their surroundings first. Dense regions get to survive first. Dense regions get to write themselves into history before diffuse regions have finished becoming anything at all. This is why those tiny points of light now carry so much more weight than they seemed to at the start. At first they looked like remarkable detections. Then they became star-forming engines, then candidate ancestors of ancient stellar fossils, then plausible contributors to ionization. Now they become something even more consequential. They become evidence that the early universe was already deciding what would count. That decision was not conscious, of course, but it was real. Physics always decides by allowing some configurations and punishing others. A region that can compress enough mass into a small enough volume acquires leverage. A system that becomes tightly bound acquires a future. A source that can release radiation effectively acquires reach. Once those differences emerge, the universe is no longer a neutral stage. It has hierarchy. That is the deeper correction to the phrase cosmic dawn. Dawn sounds even. It sounds atmospheric. It sounds like a general brightening. But nothing we have followed here is general. Everything important has been localized, concentrated, and disproportionate. Webb's result does not describe a universe gently filling with light. It points toward a universe where compact engines formed early enough and intensely enough to matter beyond their scale, inside galaxies, across reionization, and perhaps across the full age of stellar archaeology. So the dawn was not a wash of illumination. It was a map of unequal beginnings. Some parts of reality ignited sooner, some parts organized faster, some parts held together. And the consequences of those differences did not stay local. They propagated. A dense cluster changes its host galaxy. Enough such hosts alter the ionization state of the intergalactic medium. Bound stellar systems may persist and preserve the memory of the era that formed them. That chain, from compact local structure to universe-scale consequence, is exactly what makes the observation feel larger than the objects themselves. This is also why the result has a peculiar emotional texture. It is not pure awe. Awe is too generous. The better feeling is closer to recognition, the recognition that the universe has been less psychologically accommodating than we wanted it to be. We wanted beginnings to be simple because simple beginnings are narratively soothing. They imply that complexity arrives only after enough time has passed to earn it. They imply a universe whose structure grows in step with our intuition. But reality did not make that bargain. It allowed complexity to appear where conditions permitted it. It allowed influence to accumulate where density permitted it. It allowed survival to begin where binding permitted it. And those permissions seem to have emerged brutally early. That should change the way the opening image now feels in the mind. Go back to it. A distant arc of lensed light, 5 tiny knots inside it, almost nothing on the sky. At first, the image looked delicate. Now it should look compressed. Not visually compressed, conceptually compressed. Inside those tiny points sits an entire correction to how beginnings work. They tell us that when we look far enough back, we are not peering into a soft prehistory of the universe. We are watching a reality that has already begun to stratify itself into weak and strong regions, transient and durable structures, local events and cosmological agents. And once that stratification is visible, the old comfort disappears. Because the blur was doing more than hiding detail, it was hiding inequality. From far away, everything can look similarly faint, but faintness is a terrible guide to importance. A parsec-scale cluster at the edge of the observable universe can matter more to the logic of cosmic history than vast regions that never cross the same thresholds. This is one of the hardest truths in science more broadly. Systems are often shaped by the parts that are least representative of the whole, not the average region, the decisive region. The average early galaxy may not have looked extraordinary, but the decisive regions inside some of them did. And that is enough to redraw the era. JWST era review work has increasingly stressed that the first billion years now appear richer in diversity, assembly speed, and internal physical complexity than the older picture allowed. What the Cosmic Gems result does is make that revision tactile. It gives the revision a shape, a scale, a pressure. Not just the early universe was more active than expected, but this, even at that distance, even at that age, reality had already learned how to compress itself into forms capable of acting back on the cosmos. That is the matured version of the opening promise. At the start, the question was whether the universe was old enough for this. Now the question looks naive. The universe was old enough for this almost immediately. Not because time had done enough work, because the laws had. Given gravity, gas, asymmetry, collapse, and enough local advantage, the machinery of organization does not wait politely for later epochs. It begins the moment conditions permit. Webb is showing us that the moment came astonishingly early, which means the first billion years stop looking like an age of preparation. They start looking like an age of commitment, an age in which some structures were already becoming hard to undo. And if that is true, then the image we carry of cosmic history needs one final adjustment. Not just bigger, not just stranger, more severe. Because reality did not begin as a blank openness gradually acquiring structure. It began sorting itself under pressure. And in the dark, long before most of the universe became easy to see, there were already places where matter had gathered tightly enough to leave a mark that time might never fully erase. Small on the sky, dense beyond intuition, early beyond comfort. The dawn was not empty. It was already choosing, not with intention, not with foresight, but with the only kind of judgment the universe has ever possessed: consequence. A structure forms, and physics asks what it can survive. A region ignites, and physics asks how far its influence can reach. A cluster binds, and physics asks whether time can pull it apart. Those are the only questions that matter in the end. Not what appears first, but what endures. Not what glows, but what changes other things. Not what exists briefly, but what becomes part of the long grammar of the cosmos. And once you see the first billion years through that lens, the entire emotional architecture of cosmic dawn changes. Because dawn is too forgiving a word. It suggests a smoothness that the evidence no longer supports. It suggests a universal softening from dark to light, as though the early cosmos was simply brightening into being. But what Webb is beginning to reveal is harsher than that. The first light was not evenly distributed. The first influential structures were not broadly representative. The first survivors were not ordinary. The beginning was already biased toward the dense. That is the real compression line hidden inside this entire story. Not that the early universe had stars, not that it had galaxies, not even that it had compact clusters, but that almost immediately it had unequal futures. Some regions of matter were already being elevated into causal importance. Some would become engines of feedback. Some would help ionize their surroundings. Some may harden into structures that persist for nearly the age of the universe. Others would never cross that threshold. They would flare, mix, dissolve, or be overwritten by later history. That asymmetry is what makes these clusters so much larger than themselves. They are not just objects. They are evidence of sorting. And sorting is what turns a beginning into a trajectory. That is the word to hold on to now, trajectory. Because once the universe begins producing structures that can act back on their surroundings, survive internal violence, and possibly persist across billions of years, history is no longer just accumulating. It is being channeled. Some futures become easier. Others become less available. Some pathways of development are reinforced. Others are cut off. A compact cluster that blows out gas changes what can happen next in that galaxy. A source of escaping ionizing radiation changes what can happen next in the surrounding intergalactic medium. A bound stellar system that survives changes what material memory remains available billions of years later. That is not a passive universe. It is a universe already narrowing its own options. Which is why the phrase "the early universe was simple" now sounds less like an innocent misconception and more like a symptom of blurred vision. Simplicity was what distance gave us, not what reality necessarily contained. A faint unresolved galaxy can look smooth because our instruments collapse its internal contrasts. But once those contrasts begin to reappear, once compact star-forming systems emerge inside the blur, the era itself changes character. It stops looking like a soft, undifferentiated beginning and starts looking like a regime of early thresholds and unequal consequences. That is why these 5 compact lights matter so much. Not because 5 is a magic number, not because one observation settles everything, but because they make the revision visible. All the broader review language around JWST, rapid assembly, unexpectedly mature structure, physical diversity, revised timelines for early galaxies, can remain abstract until a result like this gives it a body. Here is the body, here is the scale, here is the pressure. 5 compact sources, packed into the first few 100 million years, strong enough to plausibly connect the story of galaxy formation, reionization, and globular cluster ancestry in one line of sight. That line of sight is what makes the discovery feel almost unnaturally dense with meaning. You are looking at youth. You may be looking at survival. You are looking at local structure. You may be looking at cosmological consequence. All at once. And that simultaneity should alter the scale at which the mind reads the image. Those sources are tiny, but they are not minor. They are tiny in the way a seed is tiny, small in size, enormous in implication, already carrying the logic of what may follow. That does not mean everything about later history is fixed here. It is important not to overclaim. The science is still developing. These are candidate protoglobular clusters, not final verdicts. Ryanization was driven by populations of sources, not a single spectacular object class. The responsible reading is not certainty, it is pressure. Webb is putting pressure on older, gentler models of what the first billion years looked like and how quickly dense, consequential structure emerged. And pressure is enough. Because in science, pressure is often what changes the entire map. One result does not have to answer every question to make the old intuitions harder to defend. It only has to remove enough comfort that the shape of the unknown changes. That is what has happened here. The unknown is no longer when did the early universe begin to organize itself. The unknown is how much organization were we failing to see because distance kept sanitizing the truth. That is a more severe question. It assumes the hidden structure is already there. It assumes our problem is not absence but under resolution. And once that assumption enters, everything faint in the distant universe acquires a different emotional charge. A barely resolved source is no longer a vague prelude. It may be a compressed argument we have not yet learned to read. This is the point where the entire script folds back toward the beginning. The first line said the universe was not supposed to be old enough for this. Now that sentence no longer sounds like a statement about time. It sounds like a confession about us. We were not ready for beginnings this organized. We were not ready for the possibility that the early universe had already started building things dense enough to dominate, survive, and carry their conditions forward. We were not ready for how quickly matter could stop being background and become leverage. But reality was under no obligation to match that readiness. And that is why the discovery lingers. Not because it is merely beautiful, though it is. Not because it is merely distant, though it is. But because it reveals something cold and transferable about the universe as a whole. What matters most is often not the largest region, not the average condition, not the smooth appearance. It is the place where density crosses a threshold first. That is where influence begins. That is where memory begins. That is where history hardens. And once history hardens, the rest of the universe has to deal with it. So when people say Webb is showing us the dawn of galaxies, that is true, but it is still too soft. A better reading is that Webb is beginning to show us the moment when the universe stopped being merely full of possibility and started becoming committed to certain outcomes. Committed through gravity, committed through compression, committed through the selective brutality of what can stay bound and what cannot. That is not a preface, that is already a verdict. And if those compact clusters in cosmic gems are what they appear to be, then the verdict came astonishingly early. The dark was not empty, the first light was not innocent, and the beginning was already under pressure. That is what those 5 points of light now carry. At first, they looked like distant curiosities, faint, stretched, almost decorative inside a gravitational arc, easy to admire, easy to file away as another deep field result, another demonstration of how far we can now see. But they do not remain small once you understand what they represent. Because each of those points is not just light that travelled a long way. It is light that was forced into a very small space before it ever began its journey. That is the part that changes everything. We are not looking at something that became significant over time. We are looking at something that was already significant at the moment of its formation. Already dense, already intense, already capable of acting back on its environment. Already part of the universe's decision-making machinery. And once you see them that way, the entire image tightens. The arc is no longer just a beautiful distortion. It is a wound in smoothness. A place where distance failed to hide structure. A place where the universe briefly allowed us to see not just that something existed, but how tightly it existed. Those clusters are small, but they are not gentle. They are compressions of matter and energy that crossed a threshold early enough to matter, inside their galaxy, across reionization, and possibly across billions of years of survival. They are beginnings that did not remain beginnings. That is the final inversion. We tend to think of beginnings as something that gets left behind, a stage the universe passes through, a phase that dissolves into what comes next. But here the beginning is not dissolving. It is persisting. It is shaping. It is selecting. It is carrying forward. That changes the emotional weight of time itself. Because if structures like these can form so early and endure so long, then the past is not simply something we reconstruct. It is something that remains embedded in the present. Not everywhere, but in the places where density was high enough to resist erasure. That is the deeper meaning of what we are seeing. Not just that the early universe was active, not just that it was structured, but that it was already producing forms that could survive the entire history that followed. That should alter how the mind returns to the image. Those 5 compact lights are not just young, they are ancient in a different sense. Not ancient because they are old now. Ancient because they belong to a process that began almost immediately and never stopped. The process by which the universe concentrates itself into structures that can outlast change. They are early answers to a question that has never gone away. What configurations of matter can hold together against time? And the answer, again and again, is the same. Not the largest, not the most diffuse, not the most common. The densest. Density is what allows influence. Density is what allows survival. Density is what allows memory. And once memory exists, history is no longer just a flow. It is layered. Some layers fade, some mix, some vanish. And some remain compressed into objects that carry their origin forward. That is what those clusters may become. Not just remnants, carriers. And that word should linger, because it suggests that the early universe was not simply generating light and structure, but generating continuity, building things that could move through time without losing themselves entirely. That is not a soft beginning. That is a beginning that already knows how to persist. And once persistence appears, the entire story of the universe changes. It is no longer just about what forms. It is about what refuses to disappear. Those clusters, small as they are, belong to that category. They are not the whole story, but they are the kind of structure that forces the story to be rewritten around them. And when the story shifts, the image shifts with it. The arc becomes tension. The light becomes pressure. The distance becomes compression. What looked like a faint trace of the past becomes something closer to a concentrated statement. Even here, even this early, reality had already learned how to hold itself together, which means the beginning was never empty. It was already dense with consequence, already uneven, already selecting, already shaping what would follow. And now, when you look at those distant points again, they no longer feel like fragile signals from a quiet past. They feel like something else entirely. Small, precise answers to a much larger truth. That the universe did not grow into complexity slowly. It crossed into it early. And once it did, it never went back. That is the part that lingers after everything else fades. Not the telescope, not the technique, not even the distance, but the realization that there was no long, protected simplicity at the beginning, no extended moment where reality remained gentle enough to match our expectations. There was only a threshold, and it was crossed early. Those 5 points of light are not the whole universe. They are not even a full explanation. They are something more precise than that. They are evidence that the crossing had already happened. That somewhere inside a galaxy, when the universe was still less than 500 million years old, matter had already learned how to compress itself into structures that could act, influence, survive, and carry their origin forward. And once that happens, once compression reaches that level, the universe changes character. Not gradually, irreversibly. Because from that moment on, history is no longer a smooth unfolding. It becomes layered with consequences that cannot be undone. A dense cluster forms, and its gravity persists. Its stars evolve, but its binding remains. Its radiation reshapes its surroundings. Its existence alters what forms next. Even if it eventually dissolves, it does not dissolve without effect. It leaves behind altered gas, altered trajectories, altered possibilities. It leaves behind a changed environment that future structures must inherit. Nothing returns to neutral. That is what makes the beginning feel different now. Before, It was easy to imagine an early universe that could be reset in the mind, a broad, diffuse state where details did not yet matter, where the story could be retold without consequence. Now that is harder, because if dense, influential structures were already present, then the beginning was already writing constraints into the future, already shaping what would be possible later, already narrowing the path. That is the quiet severity behind everything we have followed. Not that the universe is violent in a dramatic sense, but that it is decisive very early, and decisiveness is what removes comfort. Because once something has been decided, once matter has been arranged in a way that creates leverage, survival, influence, it does not simply return to possibility. It becomes part of the structure that everything else must work around. That is the meaning of those clusters at the deepest level. They are not just early. They are early decisions. Again, not intentional, not chosen, but real. A region collapsed this way instead of that way. A system became bound instead of dispersing. A cluster formed dense enough to matter instead of diffuse enough to vanish. And from that difference, everything downstream begins to diverge. That is how the universe writes its history. Not as a smooth narrative, but as a series of irreversible asymmetries, small at first, invisible from a distance, decisive in the end, which is why the final image should no longer feel distant. It should feel compressed, a thin arc of light, 5 concentrated points, barely visible against the dark, and inside them, not metaphorically, but physically, the conditions that help determine how galaxies evolved, how radiation spread, how matter organized, and which structures endured. All of that already present, already underway, already too late to be called simple. That is the true answer to the opening tension. The universe was not too young for this. We were too accustomed to thinking that youth meant simplicity. But the universe does not build that way. It builds wherever it can, as soon as it can, and when it succeeds, even once, the consequences propagate outward, forward, and upward in scale until they become impossible to ignore. That is what Webb has really given us here. Not just a deeper look, a harder one, a view in which the early universe is no longer a soft gradient into complexity, but a landscape where complexity appears abruptly, locally, and with enough force to shape everything that follows. A universe where beginnings are already uneven, already under pressure, already making distinctions that will echo for billions of years. And that leaves you with a final shift that does not resolve into comfort. When you look into the deep sky now, at the faintest galaxies, the most distant light, the earliest visible structures, you are no longer looking at a quiet past waiting to be understood. You are looking at a place where reality has already crossed its first thresholds, where density has already created leverage, where small regions have already begun to matter more than the rest, where the future has already started to take shape. Not later, not gradually, but almost immediately. And that is what those 5 points of light finally reveal. The beginning was never empty. It was already full of consequences.